intelligence as the future of treating neurological diseases and disorders. Neuroengineering as an area of study includes fundamental aspects of those studying the neurosciences. A particular focus on brain-machine interface, programmed with artificial intelligence, can be technologies that benefit those who suffer from neurological disorders and diseases. Brain-machine interface, as a point of departure, is where artificial intelligence is located within various neurotechnologies, such as neuroprosthetics, that can be used in medical procedures to treat the symptoms of diverse neurological disorders and diseases. In particular, today I will examine the role and the function of neuroprosthetics as they are applied in treating diseases such as Parkinson's, ALS, epilepsy, Tourette syndrome, and major depressive disorder. The ethical issues that revolve around these technologies will also be explored in order to better understand and research them in the future. I want to start off by talking a little bit about neuroscience and AI. Neuroscience, also known as neural sciences, is the study of how the nervous system develops, its structure, and what it does. Neuroengineering, then, is a particular area, applied area of science that lends its knowledge to the ways machines and technologies can be developed according to the function of the nervous system in terms of offering aid to the people who need medical intervention. Neuroscience's lens covers all aspects of structure to function, development to degeneration, in health and disease. With a focus on the brain, neuroscience wants to define who we are and what we do, which includes our memory, our brain circuitry, thoughts, and physical actions. More recently, neuroscience has become interdisciplinary to include the science of math, computer science, engineering, and the medical field, among others. The practitioners of neuroscience today must fathom and research aspects of cellular to the evolutionary to the medical realm of the ways the nervous system functions. More than before, neuroscience today integrates models and frameworks that speak of advances in artificial intelligence and machine learning toward the development of smart technologies. AI can be argued to have its origin and roots in neuroscience, the two, AI and neuroscience, developing simultaneously in order to accelerate both fields. When neuroscience is applied to AI, it will be possible in the future to unravel the secrets of human brain, such as its components that contribute to our creativity, our unconscious state, as well as our dreaming. AI began as a conceptualization by Alan Turing, deemed the father of computer science in the early 1950s. It was Turing who began to question whether or not machines could think like humans that brought forth the developments of the last decade and the categorizations of AI. It was John McCarthy in 1956 who had coined the term artificial intelligence, concretizing the technology for future exploration. In the case of neurotechnologies, akin to developments made in neuroengineering and today's neuroscience, there's a fusion of humans and machines. This fusion revolves around the bringing together of methods and tools to unite technology to the human nervous system and brain. Much of this union can now be referred to as brain-machine interfaces and the technologies that can be found within this concept. So, what are brain-machine interfaces? Brain-machine interfaces are those that most straightforwardly revolve around the interaction between the brain and the machine. They can also be referred as the brain-computer interfaces and are built on premise that sensory, motor, and cognitive information is represented in the brain by networks of neurons. Algorithms are designed to interpret their compositive electrical activity. The way neurons function can tell about how BMI or BCI work because neurons send signals to the BMI that can control the device such as prosthetics, arm, or wheelchair, or even a computer. In the case of neuroprosthetics, the non-invasive form, the brain signals can be transmitted to the machine or computer via electrodes placed on an individual's scalp. In the invasive BMIs, such electrodes can be placed inside the brain. As such, BMIs are known as devices that can enable an artificial process that allows the brain to exchange information directly with an external device. In the future, BCIs and BMIs can take on applications that will make a transformation in the ways we think about and apply cognitive prosthetics. Now I want to talk a little bit about BMIs and BCIs using artificial intelligence for the treatment of diseases such as epilepsy, ALS, Parkinson's, Tourette syndrome, and major depressive disorder. Brain activity interference based on neurotechnology can be very effective, allowing for the successful treatment of brain disorders. A neural prosthetic device is a device implanted in the central or peripheral nervous system to restore or improve lost or altered neural function. In order to further improve accuracy and reliability of such processes, For patients, enhancements from modern robotics are increasingly considered by the engineers, and tools from machine learning are expected to make neuroprosthetics adaptive and intelligent. For example, the cochlear implant, which was developed in the 1950s, was possibly the first commercially used neural prosthetics, and has helped thousands of deaf children and adults all over the world by partially restoring their hearings. From well-established results with cochlear implants to the introduction of implantable microelectrode arrays, implantable neuroprosthetic devices have gained increasing interest from healthcare professionals, scientists, engineers, and the general public. As mentioned, brain-computer interaction revolves around the technologies that can be integrated for applications in medicine and specifically for those patients who suffer from cognitive and physical impairment. It is intended that such technologies will improve the patient's daily functioning and this way of living optimally and to one's fullest capacity as an autonomous being. BCI can be used as an assistive, adaptive, and rehabilitative technology to monitor the brain activity and translate specific signal features that reflect the patient's intent into commands that operate any device. Now to talk about specific disorders, I want to start by talking about ALS. Out of the more than 600 neurological disorders and diseases, a particular focus will be on the use of artificial intelligence for ALS. ALS is a progressive nervous system disease that affects nerve cells in the brain, spinal cord, resulting in muscle control loss. The problem with the treatment of ALS is dependent on finding a novel drug treatment. Patients who are diagnosed with ALS, even though it's a really rare disease, usually die within 2 to 5 years after they have been diagnosed, and for right now, there is no effective treatment. Now I want to talk about epilepsy and its treatment with AI. Epilepsy is a common neurological condition that causes seizures on a regular basis. Seizures are brief bursts of electrical activity in the brain that cause it to function abnormally. A common surgical technique for epilepsy is the placement of temporary neuroprosthetics, which consist of subdural electrode strip, grip electrodes, or depth electrodes, reaching deep into the hippocampal region of the temporal lobe. Researchers aim to detect seizures using EEG. Most seizures are currently understood to occur when normal brain activity is disrupted by a strong, sudden hypersynchronized firing of a cluster of neurons. If a person succumbs to an EEG, a device that measures electrical output, during a seizure, the abnormal brain activity is displayed as amplified spike and wave discharges. However, when temporal EEG signals are used, it can be difficult to detect the seizure accurately, and currently, the system only works for a single patient. The technique for identifying different types of seizures across patients will then be generalized using machine learning. Researchers are attempting to take advantage of various network parameters and use them for features to train the machine learning algorithm. Researchers need to differentiate the electrical signs. They're focused on developing methods for recognizing seizures as abrupt changes in brain activity. Now I want to talk about Parkinson's and its treatment with AI. Parkinson's is a disease, which is a brain disorder that causes shaking, balance problems, stiffness, poor coordination, and difficulty walking. Medication amounts are difficult to give specifically for Parkinson's patients. Researchers aim to use artificial intelligence techniques to create a wearable device that could monitor Parkinson's disease's symptoms and possibly help treat it. Wearable sensors and Apple Watches can monitor symptoms. The wearable device records and monitors the patient's daily activities. When they take medication, it records how they react in hopes of providing a more tailored medication treatment. Subthalamic implants are another type of neuroprosthetic that is used in patients with drug-resistant Parkinson's diseases. Now to continue, I want to talk about Tourette syndrome's treatment with AI. Tourette syndrome is a disease of the central nervous system that produces physical symptoms in tics. Tics are sudden twitches, movements, or sounds that people do repeatedly. The types of tics vary, and this may mean that a person could repeatedly blink, for example, or make strange sounds without knowing they are doing so. Like other diseases, Tourette syndrome affect the nervous system. Tourette syndrome patients can today be assisted with their symptoms using artificial intelligence. Evidence of this is provided by a study conducted by Wu et al. That examines tics in Tourette syndrome patients using unsupervised visual feature learning. Scientists attempt to find an automated method to detect tic movements in people with Tourette syndrome for diagnosis purposes. They propose to use a deep learning architecture that uses both supervised and unsupervised learning methods that they hope will learn from videos of tick motion. Analyzing vocal and motor tics, researchers conducted video-based human motion behavior analysis. Their findings show that AI analyzes human behavior, movements from the videos, which also works for Parkinson's and other seizure-based diseases. Using camera monitoring systems, they could help with the help of AI record, detect, and analyze the patient's tic movements. As you can see from the graph here, this graph shows the proportion of people suffering from mental conditions like depression and anxiety and others in 8 different countries. Now I want to talk a little bit about major depressive disorder and its treatment with AI. Major depression is the most common mental disorder in the US and affects about 7% of the adults. Depression, however, is increasingly affecting at the global level, and the percentages are on the rise, as you could see from the table. Many of these people go undiagnosed, and for others, finding the right treatment is problematic. Depression is not a central nervous system disorder, but rather a disorder of moods. Depression may affect anyone at any point in their life, and it can be short or long-term, or mild or severe. While depression can be treated with medication and therapy, and has various symptoms in adults and children, ranging from loss of interest in daily activities to loss of appetite, and many others, including physical gain and suffering, it also impacts patients at social level, interfering with personal relationships. According to Stanford University professor Leanne Williams, current methods to diagnose and treat depression are imprecise at best. The questions are not specific enough in the surveys doctors administer to patients. Trial and error is predominantly the method in this case. Professor Leanne Williams argues that a new tool is needed to diagnose depression. In many cases, using the survey and trial and method approach takes time and contributes to more serious or fatal problems for depressed patients. Williams, a psychiatrist in researching in translational neuroscience, and our team developed an algorithm with the help of Professor Andrew in the computer science department to try to interpret brainwaves, especially for people with depression. Measuring brainwave patterns tells them which symptoms change with antidepressant drug treatment and whether or not the drugs are working with their algorithm. The algorithm successfully predicted whose symptoms improved while using antidepressants, but for only 7 out of possible 1,000 symptoms. Williams points out that we need new models such as this one to provide objective measures of these depression risk factors to identify people who may benefit from intensive treatments or treatments other than antidepressants, with the goal of getting the best treatment fast. Now, lastly, I want to talk about ethics in neurotechnologies. The use of AI in BCIs and BMIs, or for neurotechnologies, whether it's used for treatment of disease or perhaps to enhance human capabilities to compete or be in line with the future intelligence of AI, runs into questions. Such questions revolve around safety, privacy, and overall health, as well as other questions about humans becoming more robot or machine-like. So how far should we go when cognitive and emotional alterations of a person could result from an intervention? Which kind of risks are acceptable? Researchers help by examining the ethical issues that roll around these questions. They want to know when or if a person in a certain mental condition should be asked whether or not they choose to be treated. Is this before or after the brain stimulation has taken place? What would the family think of these decisions, or the medical system of the state in this question? One issue here is that informed consent cannot be truly informed, because no one can foresee how this treatment would work. Creating direct links between a digital computer and a brain may severely limit or suspend our capacity to control the interaction between the inner and outside world. The use of BMI on a regular basis in everyday life could be a viable source of potentially sensitive data about the neural activity. These data may be useful for study, but they also raise concerns about data about security and privacy. What methods and locations are available for encrypting and storing data? Which encryption standards should be acceptable and necessary? Who should have access to this private information? Concerns regarding malicious hacking of neural devices have also been raised, prompting requests for safe computer design principles in neural engineering. Professor Daniel LaRousse from MIT speaks of uncertainty with artificial intelligence and autonomous systems that are increasingly being applied to medical devices. Ethics issues come about when it is difficult to computationally address the real-time decision-making with AI. Because many devices, such as neuroprosthetics, rely on complex, high-dimensional input and output spaces that become safety critical when deployed in the real world, neural circuit policies can help. Task-specific autonomous systems without being dependent on large amounts of incomprehensible neural networks. Now I want to conclude my study. There's an interdependence between neuroengineering, BMI, and AI to treat neurological disorders and diseases. Neuroscience is the root research area that connects all of these fields. It shows us how the brain works and how we can advance technology in line with the brain's functions. Today, neuroscience is very important for many computers and engineering-based studies, which include artificial intelligence. When Alan Turing questioned machine intelligence in the 1950s, we can guess that he had no clue that in the 21st century, we would have more neural prosthetics to make humans think and function more like machines. This is because today we have more BMIs, which can be connected through external devices that receive messages from the brain and vice versa. Such BMIs have been integrated into medical field and technologies that assist people with neurological conditions to overcome their symptoms. For example, epilepsy, ALS, Parkinson's, Tourette syndrome, and major depressive disorder are some of the ways BMIs can assist patients in managing neurological diseases. BMIs come in various forms and can be hooked up to a brain via EEG or DBS to, for example, block tremors or other movement disorders for Parkinson's patients. The measuring of brain waves in many diseases by BMI devices that can be enhanced with AI software usually still go hand in hand with drug therapy. In this case, the AI serves as a prediction tool and collects data from patients in order to determine when and at what magnitude the onset of their symptoms will be intervened. The intervention is usually via drugs. Thus, our current use of BMIs for neurological disorders must be improved and developed, since AI alone cannot provide the needed treatment for neurological disorders. In addition to this challenge, the collection of information from AI opens up issues of ethics in neurotechnologies, mostly on the issues of safety and privacy and how they contribute to the overall health. Much research in the area of neuroengineering and neurotechnologies continues to be developed, such as with the use of neurochip, which at once bring ethical issues into question while at the same time trying to overcome them. While there's no disagreement about the advantage of neuroprosthetics, there's much more work to be done in terms of universal agreement about the benefits. Thank you for listening.
Thank you so much. That was a great presentation, and it was great. If you have any question, you can ask, you can raise your hand. I really enjoyed your presentation. Yes, Dr. Avilov, you're muted. Could you please unmute?
Dear author, could you please tell in short what technology you have used in your investigation? Thank you.
Well, I haven't done hands-on research because I work at the high school. I have worked